All right, welcome. Today we're going to pull back the curtain on the invisible world of gases. We are going to see how the totally chaotic, random dance of billions in billions of tiny molecules gives rise to the predictable, orderly laws we see every single day. It's a journey from pure chaos to perfect order. So let's dive right in.
Seriously, think about it for a second. You've got tons of metal sitting on, a bag of air, basically? So what's holding it all up? It's not the rubber, that's for sure. It's the gas inside. But how can something as light and, empty as air push back with so much force? That's the puzzle we're going to solve today. Now, you've probably run into this equation before, right? The ideal gas law. And yeah, it's a super powerful tool. It tells us exactly what happens if you change a gas's pressure or its volume or its temperature. But you know what it doesn't tell us? It doesn't tell us why. Why does it work? And that's our real mission here, to build the physics from the ground up and finally understand where this famous law actually comes from. To figure this out, we've got to connect two totally different worlds. First, there's the big picture macroscopic world. That's the pressure we measure with a gauge, the temperature we feel on our skin. And then there's the microscopic world, the hidden reality of the molecules themselves. The kinetic theory? Well, that's the bridge that connects them. So let's zoom way in. The kinetic theory asks us to imagine a gas as just a huge number of tiny, hard little spheres. They are zipping around constantly, totally at random, bouncing off each other and smashing into the walls of whatever container they're in. And here's a key idea. We assume these collisions are perfectly elastic, meaning no energy is lost. It's a world of pure, beautiful chaos.
Now, inside all this chaos, there's a really handy concept called the mean free path. Just think of it as the average road trip a molecule gets to take before it slams into one of its neighbors. It makes sense, right? The more crowded the gas is, the higher the density, the shorter that little road trip is going to be. This is one of our first real steps in putting a number on that molecular chaos.
Okay, so we've got our model of a chaotic molecular mosh pit. Now for the really big question. How do we get from all those tiny individual collisions to the steady, powerful force that can actually hold up a car? We're going to build the logic for this piece by piece. Nailing this derivation is the absolute key to connecting the micro and the macro worlds. We're going to build this argument nice and slow. First, let's just watch one single molecule hit one wall. Wham! When it bounces back, its momentum changes. Simple enough. Then we can figure out how long it takes for that same molecule to fly across the box, hit the other side, and come all the way back to hit our wall again. From that, we can find the average little push, the average force, from that one molecule. The final step? Just multiply that by the trillions of other molecules doing the exact same thing. And after all that logical work, we arrive at this absolute gem of an equation. This is the bridge we were looking for. It tells us that the macroscopic pressure, P, that we can actually feel and measure, is directly caused by three things from the microscopic world. How many molecules are crammed into the space, that's N over V, how heavy each one is, M, and, this is the big one, how fast they're moving on average, V squared. So we've just built an equation for pressure from scratch, using nothing but bouncing molecules. Now for the big reveal. We're going to take our new microscopic equation and put it side by side with that old friend, the ideal gas law. And by doing this, we are about to uncover the true physical meaning of temperature itself. Okay, look at this. On the left, you've got our new equation, built from the micro world of molecules. On the right, the ideal gas law from the macro world we live in. That K sub B, by the way, is the Boltzmann constant. It's just a number that connects temperature to energy. Now, since both of these equations are describing the exact same thing, the pressure times the volume, it means the stuff on the right side of both equations has to be related. Let's see what happens when we set them equal. And boom, this is the aha moment. This is one of the most profound ideas in all of physics, right here. Look at the term on the left, 1/2 mv squared. That's the average kinetic energy of a single molecule. This equation tells us that the kinetic energy of the molecules is the temperature. They're not just related, they are essentially the same thing, just linked by a constant. This means hot isn't some abstract idea. Hot literally just means molecules moving fast. How cool is that? And this amazing connection gives us a really practical tool right away, the root mean square speed. Because we know temperature is just kinetic energy, we can actually calculate the typical speed of a gas molecule if we just know the temperature and what kind of gas it is. For oxygen molecules in the air around you right now, that's about 483 meters per second. That is faster than the speed of sound. Okay, so temperature is kinetic energy. We've got that. But when we add heat to a gas, where does all that energy actually go? You might think it just makes the molecules move faster, but it's not always that simple. This brings us to a new puzzle. Why does it take more heat to raise the temperature of some gases than others? Well, the answer is hidden in the different ways molecules can store that energy. The key idea here is something called degrees of freedom. Just think of it as the number of independent ways a molecule can have energy. It can move side to side, up and down, and forward and back. That's called translational motion. But if it's not just a simple little ball, it can also tumble and spin, right? That's rotational motion. Each of these is a different bucket to store energy in. So let's compare. Take a monoatomic gas, like an atom of helium. It's basically a tiny sphere. It can only move in the 3 dimensions, x, y, and z. So it has 3 degrees of freedom. But now look at a diatomic gas, like oxygen, which is shaped more like a dumbbell. It can still move in those 3 dimensions, but it can also spin or tumble in 2 different ways. So that gives it a total of 5 degrees of freedom, 5 energy buckets. So why do these extra buckets, these extra degrees of freedom, matter so much? It's because of this really powerful rule called the law of equal partition of energy. It basically says that when you add heat, that energy gets shared out evenly among all the available degrees of freedom. So think of it like an energy pie. A diatomic gas has 5 slices to share the energy with, while a monatomic gas only has 3. Each little slice gets an equal share of that energy. And this whole idea of how energy gets distributed leads us straight to a really famous and testable result called Mayor's relation. It perfectly explains the difference between a gas's specific heat at constant volume versus constant pressure. And what's the difference? Well, when you heat a gas at constant pressure, you have to let it expand. Some of your energy has to be spent doing work to push the surroundings out of the way. This relationship falls right out of our molecular model. It's amazing.
Wow, we've gone on quite a journey, haven't we? We started with a simple question about a car tire. We dove deep into the chaos of individual molecules, and we came all the way back up to derive these fundamental laws about pressure, temperature, and heat. So, what are the big takeaways here? First, that the orderly world we see is actually built on a foundation of molecular chaos. Second, and this is a big one, that temperature isn't just a number on a thermometer, it is molecular motion. Third, a molecule's shape literally determines how it handles heat. And maybe most importantly for your studies, really understanding these derivations isn't just a neat trick, it's the tool you need to actually solve those tough exam problems. You know, this whole journey was built on the idea of an ideal gas, which assumes molecules are just tiny little points that don't interact. And for most situations, that works incredibly well. But what happens when you get to the extremes? What happens when the pressure gets so high that molecules are squeezed right up against each other, and you can't ignore their actual size or the little forces between them? Well, that's where the story gets even more interesting.